limits. In physics, at least, you have divergences in the specific heat. Obviously, our system is much smaller than that, just like 10 neurons. And so we look for peaks which approximate critical points. But it's a rough, it's a rough way of finding criticality. To answer the second part of your question, so I think the fact that the subcritical community was able to find success and essentially just to find success demonstrates that you don't need criticality to be adaptive. But I think that the idea is that criticality is maybe a good state to be in if you're starting to learn. And so it allows to find different solutions much quicker. So it could be that you start off critical, and then it very quickly sort of falls into a more conservative or subcritical mode. And then if the problem changes, then maybe going back to criticality would be ideal. So that's the intuition that I'm sort of going with right now, because I do believe that if you're too critical, also it might have a self-defeating purpose.
Okay, could you set up the next speaker? And before the setting, during the setting up the next one, we can take a quick question. Can I ask one? Yes, please.
Hi, thank you for the talk. Well, it's too bad the slides are gone, but in the case where you had beta equal 10, it seemed like you had another peak toward, well, not only like the subcritical peak, but like another one that was like really on the far right of the graph. Is it like, what kind of behavior would that correspond to?
That's a good question. We haven't tested the extremes, like the extreme edges. Actually, that's one of our future ideas, is to just throw beta to like 1,000, like something like that. Just go to all the way to the extremes and see what happens. My intuition is that it just freezes. So the organism is either are always turning in some direction or always moving in some direction, because at that point, the neural network will just freeze into one particular configuration, like some kind of minimum energy state, and then just not fluctuate past that. But the reason why there might be like this sort of divergence in the actual curve might be to like finite size effects, or the fact that our calculations are like they're numerical, and so there might be like large fluctuations in like it hasn't reached like equilibrium maybe. But I'm not 100% sure. Like that for me that was strange as well. I would expect it to just like fall off. So I suspect. If we ran for longer, or if we had like a larger networks, then we wouldn't observe that.
Okay, thank you very much for that talk. Okay, so the third speaker is.
So while we're setting up with this projector again, just another reminder about the poster presentations, the poster pitches. So if you have a poster in the proceedings, so it's not a late-breaking poster, but a poster, then you're going to be called up in the order of your poster number. That's different from your submission number. So if you don't know your poster number, have a look at page 35 in the proceedings and make sure you know what that number is. Because that's the order you're going to be called up in. But there'll be a piece of paper with your name on it when you're up next as well. But yeah, so just be aware of that.
projector. Sorry for the trouble. And we are rebooting the projector. It's going to take a few minutes. So, of course, yes, please.
So by taking this opportunity, I'm chairing the next poster pitch session, so I need your collaboration. As you know, poster pitch is very quick, 1 minute precisely per presenter, without any question and answer. Okay. Sometimes it's kind of difficult to kick the speaker out of the stage, so I need your collaboration. So usually, this is a place where maybe you have seen that building, weird building over there with kind of the sphere in the middle. That's the Fuji TV. In the TV industry, what they do is the assistant director is standing there, and then they raise a hand, and then you give a big applause. Let's practice. Yes. Okay. So whenever the 1 minute is around, I'm going to raise a hand here, so you give a big applause to kick them out. Okay? So please be prepared. And also, if you are giving the poster pitch, keep in mind the shorter presentation always to have a positive correlation to your poster and award score. So be concise. Okay? Thank you. Oh, great. Thank you. I can keep talking.
So that we have we need time. Tomorrow is a workshop day. There are many workshops in parallel. I think it's not easy to choose which one should attend. But one important thing is that the special workshop by LC will be held on Friday, not tomorrow. So please be sure to attend, to remember and try to think about attend the LC workshop on Friday. Also in the pamphlet, you can see the short program for each workshop, but detailed information will be on the website for each workshop. So please try to access to the website to see the detail if you are interested. Okay, so now it's prepared. So it's the last talk. The title is Integrated Information and Autonomy in the Thermodynamic Limit. Speaker is Miguel, please.
Okay, thank you. So the capacity to integrate information is fundamental for biological, cognitive, and living systems to behave as coherent autonomous units. And in this work, we want to explore what are the necessary conditions for an organism to preserve its integration as it grows larger in size, as it evolves, or as it becomes larger. And we think this is connected to different issues in transitions at in the origin of life, as how certain properties of living systems arise, or how certain types of life evolve into more complex or integrated ones. And in order to capture integrated information, we use the framework of integrated information theory, which was initially developed in the context of consciousness and provides a measure phi that tries to capture integrated information at the level of irreducibility of the causal mechanisms of a system. And it works in the following way. It gets the statistical description of a system and compares it with the same system under different partitions. And integrated information, or phi, is defined as the statistical distance between the original and the partition system, where we have two blocks that are independent, so some behavioral patterns that are complex, that are generated by the system as a whole, are lost in this one. So the distance between the two is what we measure as integrated information. And in this way, we can distinguish between systems that are integrated into coherent wholes that have a high value of phi, and systems where we can delimit different modules that have higher phi than the system as a whole, so the system is nearly decomposable. And although integrated information theory has the potential to explore different issues of biological organization, it still has some important limitation. One limitation is that it has a huge computational cost. And in the later versions, computing integrated information is only viable for very small systems, up to a dozen of nodes. And another limitation is that it ignores the coupling between systems and the environment, typically assuming that nodes outside of the system are independent sources of noise. So in this work, we use models and mean-field approximations from statistical mechanics to measure for the first time integrated information phi in systems that scale up to an infinite size, and without ignoring system-environment couplings. So for doing so, we use an Ising model, which is a paradigmatic model in physics, which describes a network of binary units that, like we have here, with positive or negative spins. And we can think of these units as cells or neurons or any other biological unit that can be either active or inactive. So we divide the system into homogeneous interconnected regions in order to apply mean-field approximations that allow us to describe the evolution of each region just by the mean activity of the components that are inside the region. And in this way, we can solve the behavior of different systems. For example, we can have a homogeneous system with just one region and a value of coupling between the components of J, and we see that we have a phase transition in this system, where we go from a disordered system with a zero mean activity to an ordered system where the activity tends to be polarized either to the positive or negative directions. And just in the middle, we have a critical point that is with a symmetry breaking point. And using the same approximations, we can try to capture integrated information in this system. And we can numerically, analytically compute what's the value of integrated information as the size of the system goes to infinity. And what we observe is that just at this critical point, the value of integrated information goes to infinity, it diverges. And this is interesting because if we have a homogeneous system that it keeps growing in size, and we want this system to maintain its integration, it should be poised just at this critical point. At least if the system is homogeneous like this. And for any other point, if the system keeps growing, it's going to lose its integration. And we can also model more complex cases, like, well, slightly more complex, like system A interacting with an environment. And we can try to measure what's the level of integrated information of system A or of the joint system A plus C, in order to see to the limit which is the most integrated unit of the system. And for different values of couplings between A and E, we can try, for example, coupling 0.8, we see that we have a critical point just as we had before, but we see that the speed of divergence at the critical point is different for A and A plus C, and we see here that the integration of A diverges faster than A plus C. And if we increase the coping, we see that the situation is reversed, and now A plus E diverges faster. And we can use the mean field approximations we use to solve the system and determine which regions of parameters allow A to diverge faster than the whole system. So we can compute analytically the speeds of the divergence and see, for example, if A is an organism, which are the conditions that allow A to be integrated in front of an environment. And finally, well, in this previous case, the environment is static, and this generally doesn't happen in nature. So we want to think how an organism can maintain its integration in front of changing environments. And for doing so, we model a slightly more complex case with a system with two regions, A and B, and interacting with different environments. And we use a genetic algorithm to tune the parameters of the system, to tune the connections of A and B, in order to maintain the integration of the system in front of these environments. And the result looks something like this. We find that the system has some inhibitory connections between A and B that compensate the changes in the environment. And if we measure the value of phi, the value of integrated information, as in the previous cases, we see that we have a diverging point as we had before, but now this diverging point is not a point, but it's a region of parameters of the environment. We see that for all these region of parameters, the integration keeps diverging. Here we plot this blue area. We have two parameters of the environment, and we see that for all this area, the value of integrated information diverges. And this is interesting because if we think of organisms that are growing and evolving, we have somehow, in order to maintain integrated information, they should be poised at critical points or critical regions. And we have somehow the internal adaptive mechanisms of a system can extend these critical points into regions where integration is maintained, when the size of the system becomes very large. And we can think about these regions of divergence of these critical surfaces as the regions of viability that allow an organism to keep its integrity, like the regions of viability that allow the conditions that keep an organism existing as it is. Well, you can check some of the details of the models and the maps in these papers, and thank you very much for your attention.
Thank you very much. Before the question, I'd like to ask the first 5 speakers of the poster pitch presentation to be left-hand side of the stage.
Miguel, can you explain again how to compute
Okay. Yeah, you basically get a description of the behavior of the system, like in the left here, and compare it with the behavior of the same system under different partitions that divide the system into two independent blocks, so the two blocks don't interact. So you compute what's the distance of the behavior of the system as a whole with the partition system. The statistical distance, yes.
Another question?
Yeah. When you compute this, you're minimizing the maximum integration partition. That means that when you find a subpartition, you can chop off to minimize phi to 0. If you now grow the network, you increase the chance of you chopping off something so that phi becomes 0. Do you correct for that somehow?
So you mean that when they grow, yeah, when...
I mean, if I just add a random node that's not connected, then I have a 0 phi because there's an integration with the thing that I just added. You have to correct for that somehow to grow a network.
Yeah, well, the thing is that, yes, if the network keeps growing, you can make partitions that have a smaller effect, so to speak, yes. And so that's why, for most of the parameters, the integration is fixed when the network keeps growing. So in order to... yes, but also as the network gets larger, if you measure the statistical distance, it also gets larger, so that compensates. But in our case, the value of phi keeps growing only if the sensitivity of the system keeps growing. It keeps being larger, which is something that happens in critical points, more or less. So in order to integration for PIP to keep increasing, you need that the system to become more and more sensitive to these changes, to these partitions. That's the idea roughly, but we can maybe discuss it later. Yes.
Okay. Okay. So thank you very much for the introduction class. And also thank you very much for all the speakers and the questions. So the next is.
Taking over. All right. So without any delay, we're going to start the poster pitch session. So as we progress, the next poster presenters, please come here in self-organized way. Hashimoto-san or Olaf, maybe. Okay, so the poster list is given in the page 35. So you have to bring up here the page 35, 36. So we will follow exactly in the same order of the PDF file to install this computer. Okay. So the first presenter is, I guess, you.
This piece of paper here, you'll need to show it to these people queuing up. So this piece of paper here is the next speaker. So when this shows your name, that means that you're coming up on stage next.
Okay. And you guys remember this thing, right? Okay. Thank you. Let's begin. All right. Alan, go ahead.
Added on in my time. So my name's Alan Doran. Tim Taylor's already talked to you about some of our work in history of technology. But this poster is actually a different project that we've been working on. A third of the food that you eat depends on bees, pollination. As you may know, bees are suffering at the moment under climate change, pesticide use, and we're actually not making things easy for them by moving to industrial-sized agriculture. So as the climate changes, a lot of our cropping is now produced indoors, and yet bees don't like the environments in which we put them, and yet we need them in those environments in order to pollinate our food. So this poster is actually looking at how we can use artificial life simulation to make big, massive impacts on food production. So it's a great way of applying artificial life simulation techniques to look outwards into industry, into a huge, enormous and very, I'd say, vital industry for human well-being. Come and see the poster.
Thank you. Next person, please.
They're not here.
Not here? Okay. Okay, let's move on to the next one. Right. Please go ahead.
Hi, I'm Anya Vastanar. I'm at Grinnell College, so small liberal arts, doing research. In general, I'm interested in modeling the human gut microbiome, so all the different ways that bacteria and viruses interact together in a very complex system, and then also interact with the human immune system. One of the things that bacteria do a lot is communicate via form sensing, and so my poster is looking at some work on first matching a type of bacteria called Vibrio harvii and how they form sense, and then using artificial life to predict how that system might then act in other environments that we were then able to test in a wet lab and match up. So that was a cool way of using artificial life to predict what a bacterial population will do. So if you're interested in bacteria, cooperation, any of those things, I'd love to talk to you. Thanks.
Thank you very much. Next, please. Next one. Yes.
Hi friends, my name is Arturo. I am a cancer researcher, and I want to know what's the deal with colorectal cancer. So, to understand colorectal cancer, first you have to understand what a colon is, because you can't understand the abnormal case if you don't understand the normal case. So to understand the normal case, we create an agent-based model where we integrated very basic data at the cellular and genetic scale of what is the gut. And the gut is composed of little crypts that replenish all of the cells in your gut. And if you have a mutation in one of these cells at the bottom of these crypts, these mutations can become cancerogenic, and then you can get a nasty tumor inside. But no one really knows how that happens, and for this we've created this agent-based model that hopefully will tell us how this happens, how the cells mutate, and how we can stop them. So come check it out. Thank you.
Thank you very much. Next.
Hey, I'm Ben Jolly from Keele University, and my poster's about, we have these very small hybrid neural networks which are really good with tasks like that require long-term deliberative planning and sparse rewards. And usually these are difficult tasks for general game players and whatnot. And we want to try take those small networks, start to generalize them while retaining the behaviors of long-term deliberative planning while still getting sparse rewards. So this is the start of that. We're taking the static motion planning network, which was used in previous work, and we're replacing it with a shallow convolutional neural network. And that now makes a fully evolvable hybrid network. And in that work, we were able to get more efficient motion planning with that, with no cost to the performance, basically. So yeah, if anyone's interested in that, come talk to me. Future work to talk about. Yeah, great.
Thank you very much. Next, please.
Hi everybody, my name is Cansu, and in this work we address the uncertainty in protein interaction network by using the computational tools. To do that, we provide a description of possible interaction of the proteins. We developed alternative models based on the plausible interaction between the proteins. By applying these models in the living systems, we see mechanistically how the environmental condition produce a change of states in organisms, especially on the protein function level. It is thought such as understanding that meaning of adaptation and embeddedness in living cell becomes apparent and more quantifiable. So if you are interested about this topic, I would like to talk to you in the poster speech. Thank you. Before I can.
Yes, Pablo.
Hi, my name is Carlos, and I have a problem. Sorry, wrong type of thing. No, actually, we have been working on a problem for several years, which is self-organization, and together with Hiroki, Justin, and Vito, we were working on a review paper about different aspects of self-organization and artificial life, which potentials it has. And probably you are familiar with self-organization. It's a common example in many models, like flocks of birds, schools of fish. You can perceive it when local interactions give rise to global patterns. So it's something prevalent, but let's say it's difficult to describe. And if you are interested in speaking about it, come and see our poster or read our papers, send us an email, and keep in touch. Thank you.
Next, please.
My name is Pablo. So we research design method applying cell growth algorithm and to achieve coherent and yet diverse design quality and still achieving adaptivity for architecture requirement. So the method is applied for the integrated project in China, and we actually that shows the kind of successful fulfillment of the architecture requirement as well. So I can talk more about in poster. And also this installation of the stage is actually next step of my research, and that's actually for the issue of the abstraction and creationality. But I want to appreciate the committee allowed me to do this experiment in this amazing opportunity. Thank you.
Thank you very much. Next, please.
Hi, my name is Colin. I work in evolutionary robotics, primarily looking at how the structure of the environment and how the structure of the robot can work together to create more evolvable robots. So in this specific task, we created an embodied version of the retina task, and we have this tree morphology that the controller is set by Hibernate. So Hibernate is special because it allows you to create these relationships by choosing different embeddings. So we created embeddings based on different relationships in the morphology, and some of them are better than others at this specific task, which has multiple objectives, local and global objectives. So if you want to learn more, come to my poster. It's poster number 9.
Hi, my name is Doug Moore. I'm a postdoc at Arizona State University. Generically, we're interested in how biological systems store morphological information. We know from experiments that many organisms can regenerate. One particular example of that is planaria, which is a little type of flatworm. We know from various experiments that we've done on them that you can modify how they regenerate. For example, cut them in half and they'll grow 2 heads instead of 1. We also know from experiments on salamanders that the nervous system plays some role in that regenerative process. And so our question is, can we build an abstract model of this interplay between an information processing system and sort of a patterning system? And the model we kind of built is called a CAN model, and it has this ability to regenerate patterns from perturbations. So if you're interested in the model and ways that we look to generalize it, please stop by.
Next, Christopher.
Hi, Christopher Nahani from the University of Hertfordshire. It's joint work with Elena Antonova from King's College London. In cognitive robotics, we put in a lot of things into robots to make them more human-like, sort of naively adding lots of ingredients, increasing the temporal horizon from immediately reactive systems to give them a more than a momentary existence. We've added self-like processes, but in the brain, there are also corresponding functional interconnectivity networks that correspond to these in the neuroscience. But there can be, for example, the default mode network, which corresponds to narrative self and narrative and self-referencing processes. There can be imbalances in psychopathology, where people ruminate or are depressed, or other kinds of psychopathology when there's too much activity or not enough activity of this network. So it's possible that the interaction of these self-processes in our robots may also be pathological, but also in contemplative neuroscience, we can see how to fix that by certain kinds of training. So orchestrating these self-processes in a balanced way is a challenge for cognitive robotics.
Thank you. Emily?
People studying evolutionary biology, evolutionary computation, and ecology all care a lot about how diversity is generated and maintained within populations. They're all studying it for different reasons and different ways, but it's the same underlying process. So we're working on a review to kind of bring together all of this research and see what these different fields can learn from each other. The goal of this review is to get a lot of different perspectives contributing to it. So if you're interested, come talk to me at my poster or elsewhere. The poster is going to summarize some of our preliminary findings so far, which include this general framework for thinking about how we measure diversity, because there are a lot of different ways that are used by different fields. I'll also be talking about when different processes act on diversity. We have this timeline here. And lastly, we'll also be talking about how ecologies are created within various selection schemes in evolutionary computation. So we're bringing it all together. Come talk to me. Thanks.
So good morning to everyone. My name is Fernando. I'm from the University of Lisbon in Portugal. So I'm presenting a poster on our recent work about the interplay between cooperation, reputation, and the complexity of social norms. So the idea is that we have a population of individuals. Each individual has a reputation, and these individuals decide to cooperate or defect with each other depending on these reputations. After each interaction, a new reputation is attributed depending on social norms, which are rules that define what is right or what is wrong, or if you wish, it defines a moral system. So there are thousands of possible norms, and some of them are extremely simple, while others are extremely complex. So first, we define a complexity measure for social norms, and then we find that there is a single norm able to promote the highest levels of cooperation at minimal complexity. And interestingly, this norm was recently found to be used by infants when they are as young as 8 months old. So come talk to me about my poster, and see you later. Thank you very much.
Hi, I'm Gabriele Valentini, and in this work we study collective decision-making from an information processing point of view. We consider a collective of agents tasked with taking a consensus decision, and in particular we look at this collective as an information processing machine, a machine that can gather information from the environment, exchange information among its components with the task to take a collective decision. We are particularly interested into how this component transfer information. And to do so, we use transfer entropy to look at the information flow when an agent applies a decision rule. We use this framework to compare two different decision mechanisms, the majority rule and the voter model. And we find that although both mechanisms have successfully solved the same problem, they are characterized by a very different information landscape. If you want to know more, comment my poster is poster P14. See you later.
Hello, I'm Hiro Izuka from Hokkaido University, Japan. Our aim of this paper is to derive the interaction rules of real fish data from captured video and to reproduce the swarm behaviors. What we did is to record the real fish data and detect the position of the fish and estimate the inputs and outputs of all individuals. And then we trained the neural network to realize the sensor model mappings. And then we trained neural network to realize that sensor model mappings, and then we performed a simulation where all individuals are controlled by the trained neural network. And then reproduce the swarm behaviors compared with the real fish data, and evaluated with some quantitative measures. And if you are interested in this work, please come to my poster. Thank you.
Next, please.
Okay, I'm Wolfgang Banzhaf. I am reporting on work with my student Hongling Bao and Khajehabodollahi. This is about a coordination game on a network where agents play this game with each other. And we throw a couple of processes in that. One is Q-learning, reinforcement learning. The second is a GA that allows the agents to inherit from their parents. And the third one is imitation that allows them to learn from the environment of other agents around them that have been successful. It's perhaps a bit of complex processes here, but it's easy to remember that's poster number 16, or 2 to 4, or 4 to 2. Just come visit.
Hi, my name is Mohamed Shahzad. I'm from Sentient Technology San Francisco. Multi-objective evolutionary optimization diversifies the solution, but it doesn't always get around deception. The problem is not all the diversity is useful in exploring the search space. Composite objectives, in contrast, focuses the search on the more meaningful trade-offs, while novelty selection effectively explores the behavior space. In the highly deceptive domain of designing sorting networks, we showed that our method can get over the local optima more consistently and faster. Moreover, without any domain-specific techniques or tweaks, we have matched all the best known results for the networks up to 19 lines so far. Therefore, the composite multi-objective novelty selection could be a good solution for deceptive domains. Poster number 17, please.
Okay, good morning. My name is Francisco Santos. I'm not one of the authors. So University didn't manage to come, but you can check his poster outside. So let me try to give an idea of the paper. So the idea is to create an evolutionary tree of scientific papers based on citation patterns. So you start from a key paper in a given field, and then you get into the offspring of each paper. So they did precisely that for ALIFE. So they started for 2 milestone papers, and they follow they analyze the unfolding of the area since the early 90s. So thank you so much.
Thank you very much. Keep that in mind. So yeah, I'm going to present one poster and then. Sorry. I already lost a couple of seconds. So this is my student Kelvin's work. So she has been working on the gene regulatory networks model, such as Stu Kaufman's random Boolean networks. What she does is to perturb those networks to see whether they can remain robust, meaning that whether they can maintain the existing attractive spaces of attraction. In addition to that, is there any new attractors that are appearing? So if that's the case, in both cases, she says it's an evolvable and robust G-related networks. In this poster, she created the hierarchical multi-layer network models and then do the same analysis. The conclusion is that if the network itself is critical as the average degree k equals 2, then the frequency for the evolvable and robust multi-layer network is going to be most frequent. So please come to poster 19. Thank you. Next, please.
Thank you. Imagine a group of embodied agents who don't know how to control their bodies, who don't know anything about their environment, and the programmer forgot to include a fitness function. How are these agents ever going to survive? Well, we have come up with a model where the agents don't need any of that. In our model, the agents make links between the external environment and their internal function. And it bundles all these links together. As a result, these agents gradually make sense out of nonsense information by forming internal decision trees. And by the way, as a byproduct, these agents evolve into predator and prey. My name is Eugene, and the prime author, Igor, has gone fishing at the fish market for sushi tonight, but he should be back for the poster. So please come by our poster at number 20. Thank you very much.
Next, please.
Hi, everyone. My name is Irina Mamayanov. Apparently. I love chemistry, especially messy chemistry. And at ELSI, we're very interested in how chemical systems can exhibit evolution. And in this work, we're focusing specifically on one aspect of evolution, selection. And one of my favorite messy chemistry systems is what's known as hyperbranched polyesters. Now, these are very interesting molecules. They share a lot of similarities with real proteins. They have microenvironments and hydrophobicity, etc. And in this experiment, we used a wet-dry cycling mechanism which actually enforces a selection pressure for certain types of hyperbranched polyester structures. Specifically, the wet phases hydrolyze linear parts, and the hyperbranched polymers tend to survive the wet-dry cycling. So we have this very relatively specific selection pressure. Come and see P21.
Next, please.
My name is Itsuki. I'm a doctor student of Ikigami. My poster is about the collective behavior of real social insect honeybees. So our collaborator develops an automatic honeybee motion tracking system like this. And so they collected the positions and the orientations of about 1,000 honeybees in the hive. So every 1 second. So we use this data and we calculated the kinetic energy of honeybees, and we found that the honeybees tend to follow the bursting behavior, and so there are two types of bursting pattern, endogenous and exogenous. So also we found that especially endogenous burst is caused by forager, which is the character of honeybees. So if thank you.
Hi, I'm not James. James is the time family matters, so I'm Moran answer. We worked on groups that collaborate, and if you have individuals in a group that collaborate with each other and you share the resources between the group members, you can get free riders because you have an organism that doesn't contribute while the group still gets payoff. That free rider gets paid. And of course, the idea is that that's terrible for evolution because these free riders just screw it up. Now, we will try to evolve, or try to investigate this a little bit more thoroughly, by evolving organisms with different payoff regimes. You can either get the payoff from the entire group, or you can share part of what the group works on with the group members, and get a small payoff respecting your individual contribution and so forth. And it turns out that free riders aren't that terrible. In fact, when you share 95% of the group effort with the group and only the last 5% differentiate between the members, you still have optimal evolution in this case. And I have 8 seconds left. Thank you.
Next, please.
Hello.
I'm Adam Stanton. I'm from Keele University in the UK. I'm an evolutionary roboticist, and for the last few years I've been collaborating with Jared Moore over at GVSU in the US on doing some work on lexicase selection in evolutionary robotics. So last year we published a paper showing that if you do use lexicase with evolutionary robotics in this particular platform that we use, you have amazing results. And this poster and the paper that goes with it are about why those results were so amazing. So we've dug into it and we've looked at it specifically from the point of view of diversity. So if you're interested in evolving generalized behaviours in evolutionary robotics, then come and talk to me about my poster number 24. Thank you.
Next, please.
Hi, my name is Jason Bernard. So behind many natural processes is an algorithm, and a lot of those algorithms can be modeled using Lindenmayer systems or L systems. So if you have a natural process and you've converted it into a sequence of strings, and those strings are symbols which allow you to recreate or simulate the process, great. Now you have the instructions for reproducing the algorithm. The question is, how can you find the right L system for a particular sequence of strings? That's what my research is on. Now, older approaches were limited to L systems that had a maximum of 2 symbols. So using some logic based on necessary conditions and a genetic algorithm, we've been able to increase that to 100% success for L systems with at least 32 symbols. So quite an improvement, and we can do that in 3.192 seconds. I'm down to 5 seconds. Evaluated on fractals and real biological systems, so if you're interested, come and see me.
Hello, my name's Joe Conner. I'm from the University of Liverpool, and my poster is on cooperation within social dilemmas, again. But this time I'm going to see what happens if you give the agents mobility. They can move around an environment. Does this affect the cooperation in any meaningful way? We found it does. In fact, it makes it lower. And we go, well, why? Why would giving them agents and wheels affect how they interact with each other? And then we found that by introducing this mobility, they will interact with another agent and then never see them again. So that ends up being a one-shot interaction which has very different... a one-shot interaction is very different from the iterated one which they have with other ones. So if you'd like to learn more, then please come find me at my poster. You'll find it's also the blue one. Thanks.
Thank you. Moving on to page 36, please.
Hello, my name is Joel Lehman, and I'll be talking about, my poster is about on the potential benefits of knowing everything. So it'd be really nice if we had a domain where we could know everything, and this is an exploration into what that sort of environment would give us. So this is about evolutionary robotics, about evolvability, about deception. So if any of those topics interest you, please come see me, poster 27. The domain is maze navigating robot in this sort of maze navigation task. We enumerate all the individuals in this environment, 43 million of them. We evaluate them all separately. And this allows us to know ground truth in this domain. And it allows us to make these sort of interesting diagrams which relate to evolvability and deception. And to get a good description of actually what's going on in the system, you should come see me, poster 27. Thanks.
Thank you. Next, please.
Yeah, so working with complex robotic platforms, it's often useful to develop these behavior repertoires that you already heard about today. So behind me on the slide here, you can see 2 examples of such posters, of such behavior repertoires. In this case, we're interested in forward momentum and turning rate, and the color represents the fitness. So we get a lot of different behaviors out of this, but generating these behaviors in this repertoire can often be difficult. So what we did in this work is look at how mutation affects the generation of these repertoires. So we compared static mutation to dynamic mutations. So if you're interested in quality diversity, come and see our poster.
Thank you.
Hi, I'm
I'm Joshua Powers. Our poster is on the effects of morphology and fitness on catastrophic interference. Catastrophic interference is a phenomenon that occurs when you're optimizing for multiple environments or tasks. As you make improvements in one of the environments, you get worse at the others. To test this, we set up an evolutionary robotics experiment with 3 different morphologies. We evaluate each morphology in a phototaxis task with 2 environments, alike to the left and right. At each generation, we combine the fitness in the individual environments for a global fitness function using the sum, the product, or the min of those fitness functions. And then what we discover is that not only does morphology and fitness make an effect, but that using the correct morphology and fitness can completely overcome catastrophic interference. We'd like to invite you to come see our poster 31, to learn more about how this happens and why it's important to you. Thank you. Thank you very much.
Hi, I'm Tomko Hashida from Waseda University. We have developed an autonomously moving pinecone robot for outdoor natural environment. This system uses pinecones as natural actuators and components of the mechanism. For this system, we focus on the function called pheromone, in which pinecones grow in humid environment and output in dry environment. And we have developed 3 types of actuators by designing the joint patterns and the interconnection systems and scales. This poster describes the characteristics of pyromorph and the design of actuators and the application for autonomously moving robots in nature. My poster number is 32. Thank you.
Hello everyone, my name is Kathleen Gabriels. I work as an assistant professor at Eindhoven University of Technology in the Netherlands, and my teaching and research focus on ethics of technology, and more specifically on computer ethics. And in this particular paper, I argue that we should not only assess a design's hard impacts, such as safety, health, environmental issues, but also a design's soft impacts, such as ethical implications, which is particularly important for AI technologies that are increasingly shaping today's society. And I discuss a number of examples where it went wrong, and also that technology is not neutral. I also offer 3 recommendations on how to broaden the agenda of technology developers with the assessment of soft impacts, and is ultimately a plea for more interdisciplinary collaborations. Thank you.
Hi, my name is Lena Vincent, and I'm interested in the origin of life. And to be a little more specific, I want to understand how a collection of living biological building blocks in a non-living configuration can transform into a system that's capable of making more of itself and responding to some kind of selective pressure. And our working assumption is that this gap can be filled by cooperating ensembles of chemicals in a regime known as autocatalysis that are spatially structured on some kind of mineral surface. So we've developed an experimental framework to test this, and it basically involves deploying an analog of experimental evolution, where we select for systems based on their capacity to respond to selective pressure and colonizing mineral surface. So if you're interested in learning more, please come check out my poster, number 34. Thank you.
Hi, my name is Manuel Bedia from the University of Zaragoza in Spain. In our work, we want to define the notion of agency in terms of the ability of a system that modulates the couplings with the environment. Also, we want to describe situations from cognitive aspects, for example, where a subject and a tool constitutes an extended device. How to do it? We propose to use integrated information theory. Why? Because we can conceptualize the ability of a system to modulate the couplings with the environment as the ability of defining integrated subsystems that connect the agent with elements of the environment. And the integrated information theory is a way for describing these levels of integration. We take these ideas in a sensory motor model. We proposed a metric for agency that, in the cases where the agents, in cases where agents conserve or maintain the boundaries fixed our metric is null. And in situations, in cases where the boundaries are changing, our
Yes, please.
Hello, I'm Motoaki from Hiroshima University, and I'm doing some research on swarm robotics. Swarm robotics is study of collective behavior of large group of robots. And because of high redundancy in number of robots, system is fault tolerant, flexible, and scalable. But if there are too much robots
investigate how this is done in a robust manner by mapping the state of the network on a finite state transducer. And if you're interested in more details, please come to poster number 37.
All right, so this morning's keynote raised this point that it's very hard to take something and write down a function that says, why is this, or is this interesting, to measure the interestingness of a sample. So we developed a method that uses a new attentional neural network to learn how to evaluate that with respect to a question. If you know the question that the network is trying to answer, it can actually tell you whether it thinks this is interesting or not, and what different things would be more or less interesting. Furthermore, if we generalize that to a distribution of questions, then we can get something like an intrinsic curiosity, where the network, not knowing what question it's going to have to answer, will rate samples based on how much their potential for helping it answer some arbitrary question in the future would be. And we can use this to learn a behavior characterization for novelty search. So this is poster number 38. I hope to see you there. Thank you.
Thank you. So me again. In this particular case, we're really interested in what's called nocturnal bottleneck transition. That happens to rodents when the dinosaurs were extinct, when they could go from nocturnal lifestyle to diurnal lifestyle. And certain rodents actually go back and forth between diurnal and nocturnal lifestyle. And the thing is that this transition is a really massive rearrangement necessary for your brain because you live in a completely different environment now. Now, we evolved Markov brains to transition from one environment to the other, and we could confirm prior results from Avida that when you transition fast enough, you evolve a brain that can live in both environments or work in both environments nicely by integrating or sharing components between both environments. Because the moment you're in a new environment, you actually have drift on the components in the other environment. You protect for this by overlapping these components. The interesting part is that in these Markov brains that we evolve one computational substrate that can actually run two different algorithms at the same time. That means that you have a universal compute architecture that can deal with both environments oscillatingly.
Hi, my name is Noriichi Hashi. We are working on with artificial life. We constructed an artificial self-replication system of RNA. Our system has two types of RNA. First is a host RNA that can replicate by itself, and second is a parasitic RNA that can replicate relying on the host RNA. We repeated the replication for many generations, and we found that the oscillation dynamics of these two RNAs. And we also found that these two RNA evolved by accumulating mutations. If you have interest, please visit our poster. Thank you.
Thank you.
Hi, I'm Peter Andrews. Now, quite often in modeling of cooperation and social systems, people use models where you have two decision options, but actually in real world institutions you have typically more than two decision options. Now, the simplest next step is to have three decision options and also to have a non-transitive relationship between these. This is the rock, paper, scissors game. Now, I used in this work the RPS game to study cooperation, and in particular I defined two versions of it where you get positive bonus if you go for the draw, or a negative penalty if you go for the draw. And I analyzed in a range of scenarios how this works. And what's most interesting that even if you have a negative draw, and even if the agents move around, you still get more cooperation than what you expect randomly. Please come to my poster. Thank you.
Thank you. Hi, I'm Pete Meltzer, and we present to you a model for simulating dynamic hierarchical biological systems. So our model takes advantage of a message passing system between layers of abstraction so that the hierarchical structure can dynamically inform the behavior of the systems that are being modeled, with dependencies both up and down the scales of abstraction. To provide detailed analysis, we integrate this directly into an industry-used graph database so that you can run complex and advanced optimized queries during computation and after computation to analyze your results. We verify the ability of our model to capture and emulate the behaviors of living systems against an existing model of tumor development in cancer growth. It's poster 42. I hope to see you there. Thank you.
Thank you very much. So here's something different. My name is Richard, and this is some work that was inspired by when I last year worked on self-propelled camphor boats, and everybody else was doing droplets, so I also wanted to do a droplet, so I dissolved some camphor in viscous oil, and that worked. It moves, and in order to make it more visible, we added some dye, and I added a lot of dye to make it look very visible. And then something new emerged, like the surprise that the complexity of the behavior increased a lot. So in this paper we have been attempting to categorize these different types of behavior and to basically get something that is programmable by only 3 different ingredients. So the camphor, the dye, and the carrier oil. So it's poster 43, come check it out.
Thank you very much.
Hi, I'm Rudra. I'm an undergrad. I work with Jim Cleaves on this project, and we tried exploring the order of emergence of amino acids in the genetic code. It's normally believed that the genetic code expanded in a non-random fashion and amino acids got incorporated by the virtue of covering the chemical space. And so Jim's previous work showed that the canonical alphabet is covers the chemical space pretty well. And so in this project, we tried to explore how well the subsets of the canonical alphabet covers the chemical space, and if we could find certain adaptive properties among the subsets of the coded alphabet as well. So my poster is poster number 44. Please visit us. We have some interesting results there. Thank you.
Thank you very much.
I'm Sina Yamasaki from Hokkaido University, Japan. I'd like to talk about studies that adversarial imitation learning causes complexity. In our simulation, but A imitates B's sounds, but generated its own sounds, not to be imitated B. On the other hand, B imitates A's sounds, but generate not imitated by B. And we express this relationship with adversarial imitation learning. Using this learning, we optimize artificial neural network of each agent. The generated sounds is shaped at first, but gradually change, periodic and chaos. And to understand what causes the complexity, we conducted experiment in different type of interaction. If you are interested in, please come to my poster. Thank you.
Thank you very much.
Hello, I'm Chris Marriott from the University of Washington. This is work I did with my student Simon DiMartini. We simulated spatially distributed agents who participated in a public goods game with local agents in their local area. We found that when the agents organized into one large group or a few overlapping groups, that defectors took over as a result of individual selection. But when they were able to organize into small isolated groups, that group selection took over and cooperation evolved. If you want to know more about our results, please check out our poster number 46.
Thank you. Next, please.
Collaboration or teamwork is a process in which different individuals group together to achieve the same goal. So in theory, it should work because everyone wants to achieve the same thing. But in practice, it rarely works. I'm sure a lot of us, at some point in our lives while working with someone, we want to strangle them with our bare hands. And one of the reasons is because one of the main reasons that teamwork doesn't work very well is because people have different personalities. And they have different ways of processing information, forming opinions, and interacting. So in order to understand teamwork, we developed an agent-based model of human collaboration that incorporates personalities of team members. So this is one of the first models that incorporate human personality in an agent-based model. So we use that to study different groups of different personalities, and then we find that our findings actually match the literature in experimental psychology. And you can come and see how you work together with other people and also other ALIFE members. Come to see the poster. It's poster 47. Thank you.
Thank you very much. Next, please.
I'm Khajehabodollahi from Tohoku University. So self-sacrifice often plays an important role in decentralized systems. So we developed a decentralized control scheme with self-sacrifice by extending the slime bot model, which is a swarm robot model inspired by chill slime mode. When an agent is not performing favorably, so the agent self-sacrifice with transferring its remaining energy to nearby agents. We demonstrated via simulations that the proposed control scheme enables the agents to perform tasks effectively under several harsh environments. And if you are interested in, please come to poster number 48. Thank you.
Thank you very much. Next, please.
Hi, I'm Tomoyuki, a doctoral student from the University of Tokyo. Our brain is composed of numerous number of neurons, and investigating a single neuron leads to understand the intelligence of artificial life. In our study, we use reservoir computing, which is a kind of recurrent neural network, to evaluate the computational capacity of a single neuron. However, to use this scheme, sorry. Please come to
Please go.
Hi, my name is Sina. I'm from Nagoya University. So in my research, I tried to test the effect of using social network services over the internet. So as a large population, we are affected by these social network services in ways that makes us interact in a parallel way. So we are introducing a temporal continuity in our interactions, also a social continuity. So in my research, I tried to test the effect of population size on the evolution of cooperation in social networks using a using a model that is derived from self-driven particle model in which agents are interact with an interaction range that is not fun. Sorry.
Okay. Right. Thank you very much. Let's give all the presenters one more big applause. Thank you so much. That's session. And here is some announcement.
Yeah, so just a quick reminder, there's the ISAL student group meeting after this happening in Mars and Venus. We're going to really start at 12:30 to give you time to go get food. But more importantly, there's the ISAL Outstanding Student Research Prize happening at 1. So please, if you're not interested in the student group stuff, come for the talk.
Thank you. Okay, first announcement, nobody moves. First, thank you for the poster. Don't forget to hang the posters if it's not done. There will be late breaking posters too. We didn't have time for those pitches, but they're there too. You'll check in right the next room to that. Very important, we're going to add 30 minutes to the schedule, so we have time to eat and things. So plus 30 minutes, so that means that the lunch is going to end at 2 p.m. and we'll start the parallel sessions at 2 p.m. and everything is shifted 30 minutes. Okay, so nobody gets lost or anything. Very important for those who registered to the cruise activity later today, don't be late. We don't really have a way to find you if you get lost. We'll meet downstairs, first floor, at 6:30, between 6:30 and 6:45. So 6:30, first floor for the cruise. Also, there are some name stickers that are available if you want to add your name to your tag. That's available at the registration desk. And thank you, and see you at 2 after lunch.
There's a registration between of the website somewhere. I can try to find the link inside. I can share it. No, it's quite open. You didn't book anything anyway.
Especially in this case. Yeah.